Okay. Welcome everyone. For the winter mini course, we are happy to have Weinan Lin, Guozhen Wang, and Zhou Xu to give a joint mini course on differentials in the atom spectral sequence and the last Kervaire invariant problem. So today and tomorrow we will have 4 talks. So today is the first one. So let's start it.
All right. First, I'd like to thank the organizers for inviting us to give this mini course on our work on computing differentials in the atoms spectral sequence. So there will be 4 talks. So the first talk today, I will give a survey talk on computing classical methods and some more recent methods on computing differentials in the atoms spectral sequence. In the second talk for today, so Guozhen Wang will give a pre-recorded lecture regarding some new techniques we developed along the way. So namely, the ones we called the generalized Leibniz rule and the generalized Mahorter trick. So tomorrow there will be also 2 talks. For the first talk tomorrow, so Weinan Lin will talk about how to use his program to do certain computations. And for the last talk tomorrow, the second talk tomorrow, and in the first half, Weinan Lin will talk about how to compute certain differentials using his computer program. And in the second half, I will talk about the final ad hoc arguments that are necessary to the solution of the last Kervaire invariant 1 problem in dimension 126. So everything is joint work with Weinan Lin and Guozhen Wang. They're both professors at Fudan University, the Shanghai Math Center. All right, so let me start. I'd like to start with my favorite question in linear algebra as the introduction to computing differentials in the atoms spectral sequence. So the question asks the following: does there exist n by n real matrices, say A1 to AN, such that for any non-zero vector gamma in Rn, I can multiply gamma with these n real matrices, and I obtain n many real vectors in Rn. So A1 gamma until AN gamma, such that they are always linear independent. So let me repeat this question one more time. The question asks for the existence of n many real matrices A1 to AN with the property that when multiply that with any non-zero vector in Rn, the resulting n many vectors are always linear independent. So it turns out this linear algebra problem is equivalent to the half invariant 1 problem, namely asking for the tangent bundle of the sphere in dimension n plus 1 to be trivial. And this is famously resolved by the work of Adams. So the only spheres that has a trivial tangent bundle are the spheres in dimension 0, 1, 3, 0, 1, 3, and 7. Okay, so the connection here is the following. If I do have these n many matrices, so first of all, I can always, so it has to be like invertible to start with. Otherwise, I can find a non-zero vector such that I multiply that, I have a 0 vector. I can always assume one of them is the identity matrix because they're all invertible. I can just multiply with the inverse of the matrix. So it doesn't change the linear independence. I can always assume this non-zero vector to have length 1, so therefore it corresponds to the sphere in dimension n minus 1. And the first matrix is identity matrix, so this is the unit vector in Rn. I can project the rest of the n minus 1 many vectors to the tangent bundle on that point, forming n minus 1 many linear independent vector fields, and giving a trivialization of the tangent bundle of the sphere in dimension minus 1. Okay, so that's the connection. So that's one direction. The other direction is harder to see, but it turns out to be equivalent to the classical half invariant 1 problem. So this Hoff invariant 1 problem has another equivalent form asking for an unstable map F from the sphere in dimension 2n-1 to the sphere in dimension n, such that when I take the cofiber, when I take the mapping cone, the cohomology ring with Z-mod 2 coefficient is isomorphic to this ring structure. So I have a class in dimension n called xn. I have a class in dimension 2n, and that is the square of xn. Okay, so of course we know that there are these four spaces, namely RP2, CP2, HP2, and OP2, giving the provided ring structure. So if we have a three-cell complex with the given cohomology ring structure as that, so in particular, we note that the class in dimension n, when we apply square n, it has to be xn squared, given by the dimension axiom in the Stingwall algebra. So in particular, this implies that square n is indecomposable in the Stingwall algebra A. The connection is the following. If square n is decomposable in the Stingwall algebra A, then we cannot have this space with a cell in dimension n, a cell in dimension 2n. We must have some other cell in the dimension between to support these operations in the decomposition. Okay, so therefore we must have square n to, a necessary condition would be square n is indecomposable in the Stingwall algebra A. So Adam told us these square n's are exactly the ones that is of dimension 2 to the m for some m. Okay. So Adams further proves that so starting from square 16, square 2 to the m square 16 is decomposable in terms of secondary cohomology operations. So if we involve secondary cohomology operations, they are actually decomposable. Then a similar argument as the one in here will show us these are on so square 1 square until square 8 are the only ones that are possible. So if you look at the first decomposable ones, we could write it down explicitly, and the first term would be square 1 multiply with this secondary cohomology operation phi 3, 3 plus other decomposable terms. So here, phi 3, 3 is a specific secondary operation associated with this Adam relation starting with square 8 times square 8. So in general, Stingwall operations are maps between Eilenberg-MacLane spectrum, and then the Adam relation can be thought as a non-homotopy of a composition of two maps between a wedge of Eilenberg-MacLane spectrum. So since we have a non-homotopy, we can define a tilde bracket, a threefold tilde bracket on it. So secondary cohomology operations can be defined, are defined by threefold tilde brackets with the Euro indeterminacy, etc. Okay, so having said that, so for the purpose of this talk, let me introduce briefly the Adams spectral sequence, and we're going to focusing on prime 2. So the E2 page of the Adams spectral sequence is X'd over the Stingwall algebra it is bigraded with S and T. So S is the homological degree and also known as the Adams filtration. So T here is the total degree, and it converges to the two primary part of the stable homotopy groups of spheres. So the differentials works in this way for the gradings. So I'm using the Adams grading. So here is the T minus S correspond to the stem. This S here is Adam filtration. So any Adams differential goes to the left by 1 and goes up by R. And now I will switch to this picture. So this is the picture, a chart of the classical Adams spectral sequence as the prime 2. So each dot corresponds to a copy of Z mod 2, and vertical lines correspond to multiplication by H0. So that's H0, so that would be H0 squared, H0 cubed. and the length of slope 1 correspond to multiplication by h1. That will be h1 squared, and that's why h1 cubed, and also h2 times h0 squared. So the feature that when I click on a dot, you can see a name and its degree, etc. This is done by put chart hem. And there are other features of this pair sequence I will show you later on are due to Wei Nanlin. So you see, this is the first non-zero D2 differential, and that's the first non-zero D3 differential. Okay, so I'll get back to that. So Adams computed that the Adams Y line, namely when S equals to 1, are given by a copy of F2 in the total degree 2 to the J, and the generators has the name Hj. They correspond to square 2 to the J in the Kervaire complex, and these are the indecomposable elements in the Steenwald algebra. So back into the chart, so the first line is given by H0, H1, H2, H3, H4, H5, and so forth. All right. So Adams proved that these Hj, they support non-zero D2 differentials, killing H0 times Hj minus 1 squared, and that is a non-zero expression starting from j equals to 4. So this corresponds to this decomposition in the secondary Steenwald algebra. So namely, Hj correspond to square 2 to j, H0 correspond to square 1, and this one correspond to this secondary operation correspond to the non-homotopy given by the Dam relation. So back into the chart. So that's the first half invariant 1 differential H4 killing H0, H3 squared. So that's H5 killing H0, H4 squared. So what I said can be made precise. The way Adams computed the D2 differentials using the secondary Steenwald algebra. So their work of Baus, Giblides, and Nassau of constructing the secondary Steenwald algebra, and later on, Dexter-Trott made computer programs can realize computing Adams D2 differentials using the secondary Steenwald algebra. So Wei Nanlin also have a computer program computing these Adams D2 differentials. So nowadays, we can even think for any spectral, as long as the secondary Steenwald algebra structure is known, then we can use these programs to compute very effectively the Adams D2 differentials. So I would call this method number 1 of computing differentials in the Adams spectral sequence, because after all, that's how Adams resolved the half invariant 1 problem. So I'm going to concentrate on the first non-zero half invariant 1 differential that H4 kills H0, H3 squared for a little bit. So there are other arguments. So for example, we could see that this element H3 survives and detects the last half invariant 1 element, and the name is sigma. In the picture, it's this element H3. So when I click on H3, I have some green dots that indicate certain multiplication relation on the E2 page. In particular, this one dot is H3 squared. So H3 detects sigma, H3 squared must detect sigma squared, and H0 times that detects twice sigma squared. So sigma is in pi 7, that's in odd degree. So the whole stable homotopy ring is graded in the commutative sense. So therefore, sigma times sigma is minus sigma times sigma. So twice sigma squared is 0. So that implies that H0, H3 squared must be killed. And if you look at the corresponding degree, there's only one dot, one possibility to kill it, and it has to be H4. So that would be another argument for the first half invariant 1 differential. So I will call this using method number 2 using homotopy relations. So this method turns out to be, although it looks very ad hoc, it doesn't explain very well why this has to be the case. It seems I'm using the logic that the only possibility to make it 0 is such and therefore forcing a differential. But in practice, this method has been very useful in all kinds of computations of differentials in spectral sequences. For example, in Tillman-Bowers computation of the homotopy groups of TMF, certain arguments are used quite often. All right, so the E2 page is multiplicative, so we have the Leibniz rule. So the Leibniz rule is also extremely useful, of course. So as the first example, you see that up to stem 13, there's no room for differentials for degree reasons, almostly. One exception would be presumably there could be a D2 differential from H1, H3 killing this dot, but both H1, H3 are permacycles, so therefore their product has to be a permacycle, ruling out this D2 differential. And now let's move on to the next non-zero half invariant one differential, that H5 killing H0, H4 squared. So it turns out we can also just use the Leibniz rule to give a proof for this differential. So there are relations on the two line, namely Hj times Hj plus 1 are all 0. And in particular, H4 times H5 is 0. So therefore, if I apply D2 on it, so it gives us 0. And here is the Leibniz rule. I'm at the prime 2, so there's no sign involved. Assume that we know the answer of the first differential. Then we know that this whole expression is 0. And we further use this relation on the 4 line that this expression is non-zero, this relation H0, H3 squared, H5. So that's in here, stem 45, 4. So H0, H3 squared, H5 is a non-zero dot on the E2 page. And there's a relation involved. It also equals to H0, H4 cube, and that's non-zero. So we can deduce the next half invariant differential. So this way we can inductively compute all the half invariant one differential. All right. So having talked about the first non-zero differential, let's talk about the second one. So namely the D3 differential in here, supported by H0, H4 killing H0, D0. So the next two methods will sound like a cheat, but that's how historically they're first done. So method number 4, I will refer this as the comparison with Toda's unstable computation. So using things like the eCHT sequence, Toda computed unstably up to dimension 19. So in particular, the stable range is known. Suppose that we know pi 14 is Z-mod 2 plus Z-mod 2 from Toda's computation. And we already know this first non-zero half invariant one differential. And the only way to make pi 14 having 2 dots left, so this dot will survive. And the only possibility is that 2 out of the 3 dots has to be killed. And by Leibniz rule, this one supports a 0 D2 differential. So it could support non-zero D3 differential, and this pair of dots killing these 2 dots is the only possibility to make pi 14 to be Z-mod 2 plus Z-mod 2. Alternatively, we could also make a comparison with the image of J. So this is method number 5. Suppose that we know J in pi 15 is Z-mod 32, okay? And we already know the bottom dot supporting a differential. And then out of the remaining 7 dots, so 5 of them must survive, okay? So that almostly give us the answer we would like to have. There are some other possibilities, but for example, this one could support a D4, I guess. With this one support a much longer differential, leaving the middle 5 to survive. But using some other method, we can probably say this dot is a permanent cycle. Then combining with that, we can deduce that these 2 D3s are the only possibility. All right. So basically combining the method number 3, number 4, and number 5, and comparing with Toda's unstable computation and with the image of J, Peter May constructed May-square sequence computing the Adams E2 page into a much larger range, and in particular use this information to deduce differentials in this range, including the D2, D3, and a few in here, and computed completely up to the 28th step. So there is a reason that Peter May didn't compute beyond that. And one of the difficult differential is actually this one, this D3 differential supported by delta H2 squared, used to be called little r. Okay, so in fact, when we encounter H5, we see whenever we encounter new Hj, we see a very long tower. And due to the knowledge of the image of J, so these differentials, the D2s, D3s, and D4s, are actually not that hard to compute with. The harder one in this range is actually this D3 differential. All right, so the next method, method number 6, I'll refer this as, so this is the Moss theorem. So in algebra, we have massive products, and in homotopy, we have total brackets. So there is a strong correspondence, okay? So if we can write down an element on the E2 or some later page in terms of massive product. So for example, this element H1, H4 in stem 16 in here, okay? So just for degree reasons, right? So this one supports a non-zero D2, so this one would support a 0 D2, but it could presumably support the non-zero D3 killing that, or support a long differential killing the top dot. But there's a way to show directly that this element is a permanent cycle. And the way to do that is to write it down as a threefold massive product on the E3 page using this D2 differential at H4 killing H0, H3 squared. So Moss theorem states that if we have a massive product and all the three inputs are permanent cycles, and it is defined on a certain page, so namely these products are 0 on that page, and we have a total bracket, assuming further that this total bracket is well defined, then the conclusion is that with the technical condition no crossing differentials, then this massive product contains an element that is a permanent cycle and converts to an element in the corresponding total bracket. So in this case, there's no crossing differential, and we can conclude that H1, H4 correspond to this threefold total bracket. And namely, in particular, proving that this is a permanent cycle. So to draw a picture, that's a picture of a threefold total bracket. The middle thing is a mod to Moore spectrum having mapped out to a sphere using this map eta and having a sigma square mapping in to the top cell. So let's look at another example, namely H4 squared. So that's the Kervaire element in dimension 30. So we can, instead of a threefold, we can define a fourfold also on the E3 page, also using this D2 differential. As a null homotopy, this whole thing is kind of symmetric. We can compute that on the E3 page, this total bracket is H4 squared, and checking the no crossing differential conditions among other things like this fourfold is actually defined, we can conclude that H4 squared is actually a permanent cycle. And that's a corresponding picture of building up this as a map between two spheres. So in history, so in fact, this D3 differential is related to this half invariant one class H4 squared. So this is due to the work of Barrett Mahoward, okay, Barrett Mahoward Tangara, okay. So in fact, combining a few methods all together, they were able to deduce this differential D3. This element used to be called little r and killing H1 D0. The idea is that they first look at this element in dimension 28, so that's D0 squared. So by shuffling some total bracket, they can prove that eta multiple on it has to be 0 in homotopy. And therefore, this dot must be killed. And by knowing all these long differentials D2, D3, and D4 relate to J, so these are relatively easy to deduce. And there are only two possibilities to kill this dot. The first one would be this D3, and the other one would be H4 squared. By building up H4 squared as a Perman cycle, so this possibility can be ruled out, and therefore forcing this D3 to support a differential on killing that. So this is an argument using combination of quite a few methods altogether. So of course, nowadays we have several other methods of proving this differential. But historically, that's the first argument. So the feature that we need to combine several methods together to prove a differential is not an accident. So let me take a small direction and mention something called the Mahoward uncertainty principles. But I guess before I do that, let me also mention that method number 7, that Mahoward proved the theorem through Braun-Gitter spectrum and prove that H1, Hj for all j are actually Perman cycles. So these are called the Mahoward E-J families. So Braun-Gitter spectrum can also be viewed as something in the middle in replacement of things like finite cell complexes like this, and building up these elements as a map between two spheres, and therefore they're Perman cycles. Right. So Mahoward uncertainty principles. So this whole business of computing differentials in the atom sphere sequence that involves a lot of different methods are guided by these uncertainty principles. And they're not theorems, they're just a philosophy. So the first Mahoward uncertainty principle states that for any spectral sequence that converges to the homotopy groups of spheres with an E2 page that can be named using homological algebra, like X over some half algebra or half algebroid, will have infinitely many non-zero differentials. So in other words, this problem of computing stable stems is not a homological algebra problem. We need other inputs, maybe even from topological inputs, to compute these differentials. So when I first started as a grad student, I consider myself very lucky, very fortunate to have the chance to talk to Mark Mahoward weekly for almost a year. I asked him, there are so many methods of computing these differentials, and what is the best method? And his answer was, well, there's no best method. We really have to combine all known methods in order to push forward computation a little bit further. So based on that spirit, so there goes the second Mahoward uncertainty principle, which states that any method that computes these non-zero differentials in such a spectral sequence will leave infinite many differentials undecided. So in other words, we should not expect to have one method that computes all the differentials. We really have to combine all the known methods. So later on, I will mention a few other methods, and in particular, Weinand's program can also compute differentials by a combination of several of the methods I'm going to discuss. All right. So getting back to the next method, method number 8. So this is the Mahoward trick. So by the way, I'm going to talk about in total 18 methods in total, and I did not mean to be I did not mean to have mentioned all possible methods in history. It's just a list of the more popular ones, so to speak. Okay, so Mahoward introduced this method, which I will refer this as the Mahoward trick. It gives a way of translating differentials and to extension problems, and also the other way around. So just to illustrate the idea, so here is the first half map, eta, and I take the cofiber, cover eta, and take the cofiber again. So I have this distinguished triangle. So the first map, of course, induces a zero map on homology, and therefore we have a short Z sequence on homology, and therefore a long Z sequence on X groups. And the boundary homomorphisms can be identified as multiplication by H1, the element detecting eta. So these three gadgets are the Adams E2 pages of the corresponding Adams spectral sequence, converging to the long Z sequence on homotypic groups. Suppose we're in the situation that for the Adams spectral sequence of Kervaire eta, there is a differential, and the source comes from the top cell, namely when mapping to S2, it's non-zero on the E2 page. And the target comes from the bottom cell, that's the image of some element on the E2 page for X, from X0. So suppose we are in this situation, so then everything is exact on the items E2 pages. But in homotypy, because of this differential, maybe suppose further that this dot and this dot, they both survive their own spectral sequences. But in homotypy, for the exactness of homotypy groups, we should expect that this dot, after the boundary homomorphism, should map to this dot on the E2 page. Okay, so this kind of phenomena is called a jump of filtration. So if there's no jump of filtration, so these two dots should change filtration only by one, and they should already disappear on the E2 page. But it could be the case that they're not connected by H1 on the E2 page, but still in homotypy, we see this connection in here. Okay, so in practice, whenever we want to apply a situation like this to give a rigorous argument, is usually we want to be able to determine the fate of all the surrounding elements in the corresponding stem and rule out everything else. And in the end, we can conclude that this dot, when multiplication by eta, must jump off filtration and goes to this dot. So later on, especially in the second talk today, we're going to give some very precise statement regarding how to generalize this Mahorver trick and using the theory of HF2 synthetic spectra. Okay, and by studying certain finite cell complexes, so Barrett, Mahorver, Tangara computed all the way up to the 45 stem. Okay, so I would like also to mention that Brunner's power operation. So these are through the quadratic construction, Brunner defined the power operation on the Adams E2 page. So one major contribution is this Brunner's differential D3 on E1. So you have in here, so that's E0. When I apply square zero, I get to E1. So the total degree will be doubled, but it still keeps the filtration. So somehow from this non-zero D2 differential of E0 through this Brunner's operation, we can prove that the D3 differential on E1 is non-zero, killing this dot H1T. Okay, so this is something missed in Barrett, Mahorver, Tangara's computation. So I'd also like to mention that using Brunner's power operation, the Mahorver eta J family, they're all non-zero permanent cycles. And if we just apply the operation, we can see that although the Kervaire classes, eventually they all die, but their H2 multiples are all permanent cycles. Okay. So the next method, number 10, I would call this comparison with TMF. You can view this as a generalization of comparison with the J spectrum. So this element G in 20,4, so the homotypy name is called copper bar. So that's detected by TMF. It's in the Horish image of TMF. So in TMF, we know copper bar to the fifth power all the way to the fifth power are non-zero. So in particular, if I have G in here, then this 40,8 is G squared, and I have 60,12 is G cubed. I can go later on in this dot G to the fourth. In particular, these are all non-zero in the homotypic groups of TMF. So in particular, in the sphere, nothing could kill them. Okay, so in particular, this is stem 80. So if you look at all these elements in STEM 81, they cannot support a non-zero differential that. Okay, so I will refer this as a comparison with TMF. So if we have a complete knowledge of the K2 local sphere, since we will be much better, we would have much more elements to compare with, and therefore reducing a lot of possibilities. Okay, so now I'm going to start talking about some more recent method. So method 11 is due to Dan Isaacson. I will call this the comparison with the motivic atoms spectral sequence. So just to give a very quick summary of the idea, so this involves the C motivic stable homotypic category. So over C, there is a Beatty realization functor taking, so in the C motivic category, there are bigraded spheres. In particular, it sends the sphere to the classical sphere, and all the classical gadgets like the atom spectral sequence and they all exist in the motivic category. So there is a motivic atom spectral sequence converging to the bigraded motivic homotypic groups, and the whole spectral sequence is trigraded, S, T, and W. So W here is the motivic weight. So what it does is it forgets the weight W over here, but all the differentials needs to preserve this weighting here. Okay, so by playing with this naturality, Dan Isaacson computed rigorously in the range all the way up to 59. In particular, there is this one new differential D3 on Q2 that kills G times T, and where is it? It's in here. So this differential is in particular very interesting that knowing that if we go to the infinity page, you see that 56 has nothing left in the co-kernel of J, and combining with odd primary computations, turns out the sphere in dimension 56 has a unique smooth structure due to the work of Kervaire and Milner, and that dimension is due to Dan Isaacson in particular because of this differential. So I would call the next one the motivic higher Leibniz rule, and method number 12. So this is done by me based on Dan Isaacson's computation. So we have the classical Leibniz rule computing differentials on a product of two elements. And if you're dealing with a threefold massey product, there is this form of the Leibniz rule. So this thing, of course, existed a long time ago. So in the classical atom spectral sequence, this formula is not very useful in practice due to indeterminacy. So you see that this formula is that this expression belongs to the sum of three sets, and all of these three things could have a large indeterminacy, making it not practical classically. But motivically, since everything is trigraded, actually making the indeterminacy smaller and making this formula more useful. So based on Dan's computation, I deduced a D2 differential on this element, capital D1, and that's this element in here. So at the time, that was the only argument. So this D1 has a threefold massey product, goes to this starting here. Motivically, it supports a non-zero D2 differential, and therefore deducing this non-zero D2 differential. So nowadays, of course, we have many other arguments. In particular, the secondary stimuli algebra would give a direct argument for this D2 differential as well. So moving on, so this D2 differential also have a very interesting proof recently by William Balderrama using comparison with the unstable atom spectral sequence. So William posted a 2-page paper on his website. You should take a look. This is a comparison with the eCHT argument, and it's very interesting. So as guided by the second Mahoward uncertainty principle, so Isaacson's motivic computation got stuck around dimension 60 and 61. So Gordon Wang and myself, we have this RP infinity method based on the Karn-Priddy and algebraic Karn-Priddy Lin theorem. So the Karn-Priddy theorem states that this transfer map from RP infinity to the sphere is surjective on positive stems. And Lin further proved that it is a surjective map on the E2 page. So therefore, this motivates us that if we wanted to study a differential in the sphere, we should go back to RP infinity and study the subquotients of RP infinity. So, so in particular, this allows us to prove this one differential by going through some subquotients of RP infinity, this element capital D3. And there's a consequence of this differential, which is that on the 61 stem, so on the infinite page, there's nothing left. And by the work of Kervaire and Milner, and also combination of earlier odd primary computations, together with two other differentials, we also conclude that 61 sphere has a unique smooth structure. This one turns out to be the last odd dimensional case. The only odd dimensional ones are 1, 3, 5, and 61. So later on, we have this multiplic Kervaire method by Gregory, Addison, Wang, and myself. So the quick summary is here. So for the multiplic category, if we consider modules over the completed sphere, and if we invert tau by theorem of Darger-Isaacson, this is the same thing as the classical stable homotopy category, completed at a prime p. And if we mod out by tau by considering the modules over Kervaire tau, a theorem of Gregory, Wang, and myself, we prove that this is equivalent as a stable infinity category to Halley's derived category of BP star BP comodules. So you can view this as a deformation of categories inverting tau and mod by tau. In particular, it also gives us a deformation of spectral sequences. So inverting tau, getting us back to the classical atom spectral sequence, modding out by tau give us the multiplic atom spectral sequence for this Kervaire tau, this two-cell complex. So through this theorem, this can be identified as the algebraic Novikov spectral sequence for BP star, which is a trigraded spectral sequence converging to the classical Adams Novikov E2 page. So the point here is that this right-hand side category is algebraic. It's a derived category of an abelian category, and therefore this whole Adams spectral sequence is algebraic. So Gordon Wang made a computer program which computes differentials in this spectral sequence completely up to the range. It's very effective. So now whenever we have a differential here, we can put it back to the middle and then further push it to obtain a classical differential in the Adams spectral sequence. So for example, this differential I was just mentioning on the 61 stem. So this differential took us more than 40 pages to prove it using the RP infinity method. Now using this multiplic Kervaire tau method, it's just the computer output. Okay, so combining with many ad hoc arguments with Isaacson, we computed almost all differentials up to the 90 stem. So one differential I like to draw your attention to in particular is this D4 differential on H5 cube. So this one is again an algebraic Novikov differential. It's a computer output. So this differential is in here. So recall that there's a relation H4 squared H6 is H5 cube. So that's the non-zero D4 differential hitting the start. So it is interesting, of course, because it's a power of Hj, and we know that Hj to the fourth power are all zero starting from H1. So later on, by comparison with the synthetic atom spectral sequence by Birkeland, Isaacson, and myself, so I will say more about what the synthetic category is. So we were able to deduce, for example, in particular, this element in stem 83 supports a 0 D9 differential. It's somewhere in here. Okay. Well, I guess the computer program doesn't know this differential. That's the great thing about this synthetic argument. So our current computer program does not know about this differential. You see that it marks D9 on this element is question mark. But this synthetic method, the three of us can prove that this one is actually a D9 cycle, and there's no other possibilities. So it turns out this one is a permanent cycle. So before I say more things about the synthetic method, a remark here is that a combination of the motivic method and the synthetic method. So Robert Birkeland and we prove that the HJ cube all supports starting from J equals to, I guess, previously 5 and now starting from 6. They all support a non-zero D4 differential. And the target has this same form H0 cube times GJ minus 2. So that's the first non-zero D4 differential in this family. That's in stem 93. And the next one is in here, and the computer program doesn't know about this one either. That's the differential H5 squared H7 or H6 cube. That's in stem 189. Okay. Of course, the good thing about this family is this is a computation for all J when J is large enough. Okay, so now I like to say a few words about synthetic spectrum. So the theory of synthetic spectrum, also known as filter spectrum, are introduced by Pius Rogovsky and also by the work of Gregory, Isaacson, Cross, and Rika. It's an analog of the C-motivic cellular category. So there are also bigraded spheres in this category, and there's a parameter which I call lambda just to make a distinction versus tau in the motivic setting. So when we invert lambda, we get back to the classical stable homotypic category. When we mod out by lambda, namely considering the modulus over cofiber of lambda, which is a two-cell complex and also an infinite ring, this is the derived category of the comodulus over the dual stimuli algebra. So this category has many features in analog of the motivic situation. When you consider the bigraded homotypic group of cover lambda, so this is the classical Adams E2 page. In the motivic setting, the bigraded homotypic groups of cover tau is the Adams Novikov E2 page. So you can view that the C-motivic cellular category as a categorification of the classical Adams Novikov E2 page, while the HF2 synthetic spectrum as a categorification of the classical Adams spectral sequence. So the synthetic Adams spectral sequence converging to the bigraded synthetic homotypic groups of spheres is rigid in the following sense, as in analog to the motivic Adams Novikov spectral sequence converging to the motivic stable homotypic groups of spheres is also rigid. So first of all, it is a lambda Bach-Stein spectral sequence. So what do I mean by that? The E2 page can be written down as X over A, adding lambda as this one parameter polynomial algebra. Here X over A is the classical Adams E2 page. And whenever we have a classical differential dr of X killing Y, then synthetically, we have a dr differential of R killing lambda to the power of R minus 1 times Y. So here are some, so the pattern of differentials, they determine each other. And this whole spectral sequence is a Bach-Stein spectral sequence. So here are some examples, okay? So that's the first two non-zero differentials in the classical Adams spectral sequence. So let me get back to the chart. So classically, we have this D2 differential, H4 supports D2, and H0, H4 supports a non-zero D3. So synthetically, since this is a D2, it kills lambda times that. So H0, H3 squared is still non-zero in the homotypy. It is just that it's a lambda multiple. It's a lambda torsion, single lambda torsion. Similarly, H0, D0 is still present in the synthetic bigraded homotypic groups, and its lambda multiple is also there, but lambda squared times it would be 0. So that's what happens in the synthetic sphere. But we can also consider the synthetic sphere mod out by lambda. All the non-zero differentials, because there is a factor of lambda, they all become 0. And in particular, the bi-grid homotypic groups is a classical E2 page. We can also consider things like mod lambda squared. So we have this D2 differentiating lambda times that, then its lambda multiple, lambda H4 should kill lambda squared, H0, H3 squared. But lambda squared, this expression is already 0 on the E2 page for this gadget, and therefore the D2 differential will be like this. So as you can see that in the sphere modeled by some power of lambda, not only the target will have some leftovers, some lambda torsion there, also the source will have some leftovers. So these leftover information are especially useful because it is still the bi-grid homotypic groups of the ring. We can still do all the classical ad hoc arguments like shuffling total brackets, but with these elements being non-zero. So in particular, we see that the homotypic groups of S mod lambda to the n, they encode the atoms in +1 page in a precise sense. So this can be stated very precisely. And furthermore, if we consider cofiber sequence, multiplication by lambda to the n, and forming the cofiber in here, so this boundary homomorphism, it encodes total atoms differential information. So for example, if I just take n equals to 1, so in here, that's S mod lambda, its homotypic groups is the E2 page. So H4 is a legitimate homotypic class in here. It doesn't survive in the sphere because it supports a differential. And therefore, by exactness, it must map to something non-zerally to the homotypic group in here. And by checking the corresponding bi degree, it is given by the Adams differential resulting in here. So this information turns out to be very useful in translating differentials to extension problems. So having these two observations, we can make some further observation. So now any element on the Adams EN page is an actual homotypic class, and therefore, so before that, when we talk about naturality, we're only allowed to talk about elements survives to the infinite page from a spectrum X mapping to a spectrum Y, and talking about this kind of jump-off filtration phenomena. But now we can talk about this on any Adams EN page, this naturality and jump certain filtration. So therefore, we can talk about these extension problems on a given page. Another thing is that these total differential information can also be translated into extension problems, as in maps between bi-graded homotypic groups. So based on that, we introduced two new methods, which we call the generalized Lambda and the generalized Mahorber trick. And we need certain technical no-crossing extension or differential conditions to make them true. So I'd like to mention that various versions have been introduced by various people, namely Behrens, Birkeland, Schwa, Ma, etc. So our technique have some new feature. First of all, we introduced these technical no-crossing extension and differential conditions to guarantee that the statements are very precise and true. And another thing is that in the classical Mahorber trick, so usually the source and target, when we talk about comes from top cell, bottom cell, they usually preserves the atom filtration. It comes from the exactness on the E2 page. We allow jump-off filtrations, so therefore they're more applicable in many different situations. And we then make computer programs to carry these things out. So to explain the rough idea, so in the second talk today, in Guozhen's talk, you hear details of the statements with examples of the generalized Lambda and generalized Mahorber trick. But let me just say this very briefly. So suppose we have a map from X to Y. So usually when we want to apply naturality to deduce a differential from X to a different in Y, we want these two elements to preserve the degree, and therefore we can apply naturality. But now we allow these two elements, they're an element on some EN page, so therefore lives in the bi-grid homotypic groups of cofiber of lambda to some power, and we're allowed to talk about this kind of jump-off filtration phenomena. And whenever we can make that precise, and there's no crossing phenomena, then we can deduce the differential in Y. So in some sense, it can also be called the generalized naturality, if you like. And the sketch argument would be a differential correspond to this total differential, this boundary homomorphism in this covariable of lambda to the n, and we're dealing with the commutative diagram, essentially. And the no crossing conditions guarantees that when we talk about the associated graded, we're landing on the right side. So here is one example. You hear more details in Gordon's talk. So suppose that we start with the half invariant one differential here. So let me get back to this chart. So this is a D2 differential. So namely, so you can compute that with the secondary stimuli algebra, if you like. So we like to deduce from this D2 differential to this non-zero D3 differential. So this, you see that the sources are connected by H2, namely multiplication by nu. So if we know somehow that this dot times nu is this dot, then we're good, right? Classically, we cannot do this because one is a D2, the other one is a D3. There is a jump of filtration, and also because these two dots are killed, right? So we're dealing with 0 times something is also 0. But synthetically, there are leftovers. This D2 differential leaves this dot still there, but it's a lambda torsion. This dot, if it happens, it will still be there, and it's a lambda square torsion. So in particular, times lambda is still non-zero. And we could talk about in the sphere whether or not this dot times nu is lambda times this dot. So suppose we know that, right? Suppose we do have this new extension from this target to lambda times the other target, then we can apply the generalized lambda rule to obtain from this D2 differential to this D3 differential. And how do we know this extension? Well, that's the generalized Manhover trick. So we started the cofiber mu, and turns out there is a D2 differential making this connection. So this element on the top cell kills this expression on the bottom cell. So what I'm doing here is that I can use the secondary stimuli algebra to compute these two differentials, one in the sphere, one in Kervaire nil, and using the Manhover trick to translate this D2 differential into a non-trivial extension and combining with the generalized Leibniz rule to deduce a non-zero D3 differential. And all of this can be automated by Weinand's program. So, and that's the picture for the generalized Manhover trick. We have a non-zero differential when the source and target that comes from two other dots, and we're allowing jump-off filtrations going on here. And the conclusion is this extension problem from X to Y. Okay, so you hear in Weinand's talk that so basically we're studying many spectrum, and so Weinand's program does a bunch of things. It computes the atoms E2 page very effectively. It also computes a bunch of maps, and also we are studying there are programs studying cofiber sequences. So we're considering many spectrum. We're considering the sphere, we're considering the cofiber of the Hopf maps, we're considering certain 3-cell complexes, 4-cell complexes, we're considering the smash of a bunch of things. For each one of them, we compute the atom E2 page and also maps among them. So for example, so that will be the picture for Kervaire nil, and we can consider map from the sphere to Kervaire nil. So you see on the screen, the right-hand side is the top cell. It's a single sphere. The right-hand side is Kervaire nil. So if I zoom in, I know each dot on the Kervaire nil whether or not it comes non-zeroly from or mapping non-zeroly to the top cell, etc. So we're studying these maps as well. We're applying naturality and so forth. We also involve a bunch of RP infinity subquotients, certain spectrums and computing differentials there. And then Weinand's program can compute cofiber sequences and can apply these generalized Leibniz rule and generalized Manhover trick effectively and deduce many differentials for the sphere. So knowing enough information around dimension 126, we were able to deduce that theta 6 H6 squared survives in the atom's spectral sequence, and by theorem of Browder, that corresponds to the existence of free manifolds of Kervaire invariant 1 in dimension 126. So in the last minute, I'll just say the sketch proof, which will be expanded in the second half of the last talk tomorrow. So Barrett, Jones, Howard had this inductive argument trying to establish the existence of all theta j. Namely, if theta j exists, there is a theta j has order 2, and with the square being 0, then the next theta j plus 1 exists and has order 2. Of course, we know this inductive argument have to break it down somewhere because theta 7 does not exist due to Hill-Hopkins and Ravenel. So upgraded this feature in the synthetic setting, Berkland and I proved that H6 squared survives if and only if this expression, so lambda here is the synthetic parameter, and theta 5 is any synthetic lift of theta 5. So this expression in stem 125 is 0. So we actually have an estimate. So theta 6 survives to the ER plus 3 page if and only if this expression is 0 in S mod lambda to the R. So using the knowledge at the time writing the paper, Berkland and I proved that theta 6 survives to E9 page. But now we know much more in the corresponding range. So let me show you the picture. So around here, if we go to the infinity page, so first of all, we do not know everything, right? For example, if I click on this dot, I do not know what happens to D6, so meaning that it survives the E6 page. Like this dot, it survives the E12 page and etc. The computer program only knows this theta 6 survives to the E7 page. So there are a bunch of dots that are all presumably could be the target in dimension 125. But this inductive argument builds up this connection of the differential supported by this H6 squared with eta times theta 5 squared. So we can first estimate what is the lowest filtration for theta 5 squared, and it turns out to be this dot. So it has to at least have filtration 10. And if we go to 125, this dot, we do not know precisely D4, but we do know it has to be non-zero and killing a combination of these two dots, leaving the remaining one to be an element in the Hurwitz image of TMF. So this top dot doesn't matter. And so the only possible eta extension, so we have to be careful about all the lambda torsions, namely the residues of all the differentials, because when we deal with synthetically, we have to deal with that. But just roughly speaking, the idea is that if this element were to detect theta 5 squared, and that's the only possibility for non-zero eta extension. So all we need to do is to rule out this eta extension to have the argument. So otherwise, that would be a non-zero D12 differential. So we reduce this to a 2 extension between these two dots, and we prove a new extension between these two dots, and there's some other ad hoc argument to rule that out in the end for this 2 extension, which allows us to deduce that theta 6 survives. So I'll say more details in this part tomorrow. So let me end with some future goals. So what we still do not know is that we do not know whether or not theta 5 squared is 0. There are still a bunch of possibilities. We do not know twice theta 6 is 0 or not, although it seems that it's going to be very likely that theta 6 has order 2. And we do not know explicit differentials on H7 squared. So that will also be a future goal by running the program further, and hopefully knowing the explicit differential on H7 squared will allow us to know more information on what's going to happen for later on differentials on all the theta j's. All right, I'll stop here.